which apparently will not adopt the QServe. So, and we're about to submit our work plan for the next year. So, and just to mention that the reason I got late is because I was at a meeting of the LSST Corporation, which just finished. So I apologize for my tardiness. But I mean, if you want more information, we can stick around after the presentation and we can talk, okay?
Yeah, that's interesting. Thanks, I appreciate it.
Yeah, sorry I didn't turn my camera.
Oh yeah, no worries. Hi.
Okay.
Yeah.
Okay, I mean, we can stay a little bit longer after the talk, okay?
Sure, thanks.
Okay. I think people are still joining us, but I think we can start. So let me do a short introduction and then I will pass you the floor, okay?
Sure.
All right, so well, hello everyone, and welcome to another talk in our webinar series. Today, we have the pleasure of having Raen from the University of Pittsburgh. He's a graduate student and researcher in physics and astronomy, and he's interested in large-scale transient and variable star classification and statistics. He's also lead and developer for the Pitt-Google broker, whom he's going to talk about today to us. Before we start, a quick reminder, this webinar is also being streamed live on YouTube. You can find the link on our website or access it on our YouTube channel, LIneA MCTI. Troy, thank you very much for being with us today. The floor is yours.
Thank you. I appreciate it. Thanks for the introduction and the invitation to speak here today. Okay, can I just confirm that you can see my title slide here?
Yes, we can see it.
Perfect, thank you. Well, as Rodrigo mentioned, I am Troy Raen. I'm a grad student at the University of Pittsburgh. I'll be talking to you today about the Pitt-Google Alert Broker. We are building a 100% Google Cloud-based alert broker. And so I'll talk a little bit about what that means here. Here's our collaboration. This is the core group of people working here. I am the lead developer. I'm a grad student in my final year here, so I'm about to enter the job market. Starting to think about some of that kind of stuff. Here's where we are headed today. So first, I will talk a little bit about our broker's motivation for existing. Then I will do a little comparison of the different broker approaches and how that ties into basics of the cloud model. Then we will look at the Pitt-Google broker architecture and some of the Google Cloud services that we employ to run this broker. And then finally, I will talk about just a couple of other tools of interest, I'll call them. These are things that I have seen available on Google Cloud that I'm interested in, but I haven't tried out yet. And these may be things that you all are interested in terms of your IDAC development also. So I'll try to highlight some of those at the end. The bulk of the talk will be here in 2 and 3. Number 1 and 4 will be pretty quick here. In terms of what I'd like you to be able to take away from this talk, one is just understanding the cloud model, what the cost-benefit trade-offs are. And 2 is if you learn about 1 or 2 Google Cloud services that sound interesting to you and you can understand and describe either how we are using them or how you might use them in your development of an IDAC, then I think that I will have succeeded here today. Okay, in terms of our broker's motivation, so maybe I should, so let's see, I see that you have had several other brokers come and give talks already, and so I have assumed that you know what an astronomical alert broker is, so I'm not going to go into details about that. I'll just jump straight to why did we decide to build an alert broker, and what is kind of different about us. So our main motivation really was to get the data into Google Cloud so that anyone and everyone can access however much they want of the data and do whatever they want with it. The LSST project is not scoped for this. And so this was a need that our PI, Michael Woodbasey, and our contact at Google, Ross Thompson, got together and said, hey, LSST is not actually scoped to just provide all of this to everyone in this way. So let's get it onto Google Cloud and let's just make it available. And let's make it available for people to play with a lot of the tools that Google Cloud offers. I'll stress at this point that the data is not tied to Google Cloud. So we are operating 100% on Google Cloud, but users can certainly query and pull that data off into anywhere they want. So a couple of caveats I have to mention with this, and I think they're totally reasonable. One is internet access is required, but actually no other hardware or software is required. You can do all your compute on Google Cloud if you want. If you have your own big compute, you can certainly access and pull data and do your compute on your own machines. The other caveat is that everyone pays for what they use. So this is a different pricing structure than any other brokers use. But in order to provide this to everyone, and this is part of the Google Cloud model, is that everyone pays for what they use. So a couple of our specific goals here. One is to enable scientific collaboration by getting the data in here to Google Cloud, as I said, and letting people play with it, and doing some specific things that will support the scientific collaboration on this data. One of those things is that our pipeline model exposes the data publicly at every step of the processing pipeline. So users can actually access data that is pre-processed to a level of their choosing. If somebody wants to listen to the entire full LSST alert stream, they can get that through us. Or they can listen to some downstream steps and get data that is processed a little bit more and maybe more specific to their science area. And three here is to use Google Cloud Services to maximize the efficiency of our broker and minimize the effort that's required to develop, run, and support an alert broker at LSST scale. So of course, LSST scale means that these alerts will be coming in at a rate of about 10 million per night. So this is a lot of messages coming in here. Okay, so a little comparison of broker approaches and how that ties into the basics of the cloud model. Other brokers also run in the cloud. And so you may have heard this when you've heard presentations from other brokers. This can actually mean anything from something as simple as they've just moved a single component of their pipeline or data storage onto the cloud. So maybe they've just moved their object storage onto the cloud. Or this could mean anything from there all the way to 100% Google Cloud, or excuse me, 100% cloud-based, not necessarily Google Cloud-based, but some cloud. That's their whole pipeline, database, object storage, everything is in a cloud, is running in a cloud. So the Think broker is operating on an OpenStack-based cloud in France, and they cite some of the benefits of cloud computing here, scalability, cost effectiveness, fault tolerance, things like this. So what makes us different? Well, we actually have a fundamentally different broker model that is based on Google Cloud Services, and I emphasize the term services, and event-driven processing. So I'll talk a lot more about what those two things mean. We will start with Google Cloud Services. So cloud services in general, when you're doing cloud computing, users rely on the cloud provider to manage the physical hardware and support access to it. And so all of these things are services, but the level of support can vary greatly. So kind of at two extremes here, you can rent VMs, in which case you have a lot of control over your application, but you also have a lot of responsibility. You write both the application code and you manage the VM environment, the containerization and deployment, you manage all the scaling, the fault tolerance, everything else. Google manages the physical hardware. So that's at kind of the low service end. At the high service end, we have something here called Cloud Functions. This is serverless computing, where you can write the single function, maybe it's a Python function that you want to analyze your data. So you have an alert coming in. I want to process that data through this simple function. I can just write the function and deploy it to the cloud. And then Google manages everything else. They manage deploying, scaling to meet the demand of the incoming alerts, the fault tolerance, and everything else. So the user trades some control and responsibility for ease of use. So when the Pitt-Google broker takes advantage of these services, what I'm specifically talking about is these more highly managed services and not VMs as much as possible. So this actually results in a lightweight pipeline that's highly modular. We are nearly serverless, and we don't have any direct responsibilities for data storage, data delivery, and things like that. The compute scaling, et cetera. So this is a bit of jargon, serverless. What does that really mean? I mean, everything runs on a server somewhere, right? And so all of these things are actually running on servers. But what it means to be serverless is that the developer, in this case us, is not concerned with managing the containers, the VMs, or the physical servers. So the developer doesn't have to be concerned with any capacity planning, configuration, management, maintenance, fault tolerance, scaling, all that kind of stuff is handled by the cloud provider. So let's look at some different models, design models that brokers use, that specifically astronomical alert brokers use, and how that ties into running in the cloud and different ways to run in the cloud. So on the left end here, we have a design model that is run the whole end-to-end pipeline on a single device. And this may not include persistent storage. You're just processing the incoming alerts, running your full pipeline on some single device. This single device might be a server or a VM, or in the case of the Bob alert broker, they run on a Raspberry Pi. That's a really interesting broker model that they are working on there. In the middle here, we have this is brokers such as Antares and Think. And the idea here is to package the broker into multiple containers and run those containers on clusters of VMs. So you might have a container that packages your data pipeline, your science processing pipeline, a different container that packages your persistent storage, another one for communication and stream ingestion. You package that all up, you run clusters of VMs to do this. Over here on the right, we have a design model that is to run the broker on Google Cloud, or excuse me, I keep saying Google Cloud. In this case, I just mean generically cloud services. So you can run the broker on cloud services. So the services might include some really modular data processing. I'll talk more about what I mean by that. Persistent storage, communication, VM management, user accounts, and data access. So some of these things are really quite one-to-one comparison. The difference is here in the middle, the broker is packaging the containers, running the clusters, managing those clusters and VMs. And when you do it here on the right, you are letting the cloud provider manage most of that infrastructure for you. Okay, so we'll look at kind of types of software and services that brokers use, and then I'm going to map these to the design models here. So sort of three different categories. Oops, excuse me. And these are kind of rough categories. First here on the left, this is software that the user directly downloads, manages, and runs. So this is like a Apache Cassandra database, Apache Kafka, which is a message streaming platform, Apache Spark, MongoDB, Kubernetes. These are all things that other brokers use to run their brokers and do their data storage and catalog queries and things. In the middle here, we have services that manage and run the traditional software in the cloud. So you can use a cloud service that manages a Mongo database. You can use a cloud service that manages your Kubernetes, and Kubernetes is a platform that manages containers and scaling and deployment and things like that. So you can basically take this, what I'll call more traditional software, and use a service that runs that software in the cloud, so that it abstracts away some of the management and things like that. All the way over here on the right, we have services that are built explicitly for cloud computing. So in contrast to the services here in the middle, which take traditional software and run it in the cloud, these are services explicitly built for cloud computing. So this is like Google PubSub, BigQuery, and Cloud Run. These are all things that we use, and I'll talk more about what they are as we go. So how do these things map to each other? In other words, what's the relationship between the design choice that a broker might make and the software services that they use? And so that's what these arrows represent. So if you're running on a single device, you will use some traditional software. You might even use you might even run in the cloud and use some service that manages a little bit for you. And actually same with this design choice here in the middle, where you're packaging into multiple containers and running on clusters of VMs. You'll use the same types of traditional software. You might be more inclined to take advantage of these cloud services that run this software in the cloud. Over here on the right, if the design choice is to run the broker on explicitly cloud-based services, that can mean kind of two things. You can use these services that run traditional software, or you can use, you can use these services that are built explicitly for cloud computing. So here's where I think a good visual distinction of what is different about our broker than other brokers. We sit here, and we are the only community alert broker that sits here. Excuse me. Other brokers do something in here, and they may even run the broker on cloud services to some extent. So some of this is in their box, and maybe one of the specific things that they might use is VM management. So this is like Kubernetes engine or something like that. But we are the only broker that sits here and really uses explicitly cloud-based services for this type of compute. Okay, so let's talk a little bit about the Google Cloud model and what that means. So a lot of these things are different from how other brokers handle this, and how other brokers' users interact with the data in the broker. So for us, for the Pitt-Google broker, we store data in Google Cloud Services. So BigQuery, PubSub, Cloud Storage, these are all cloud services where we are letting Google Cloud manage the data storage, the delivery, the user accounts and credentials, and all those management type things. So for a user to access the data, they first create an account and obtain credentials from Google Cloud. It's a free account. It's a simple setup. You can get a project going in under 5 minutes. And you don't need to contact us at all, you meaning the end user. By contrast, other brokers manage their own data storage and delivery, their own user accounts and access. They are not using these explicitly cloud services. Even if they are running in the cloud, they are still managing their own data and their own access. So that is one major difference with us versus other brokers. So how do users access data that is stored in these Google Cloud services? There are two main ways. Number one is API access. All of these Google Cloud services have well-developed and supported APIs. There are REST APIs, there are client APIs, Python client, Java client, things like that. There is command line access. And through these APIs, you can access from anywhere. So you can access if you're operating in Google Cloud, or if you're operating on your own compute, your own personal laptop, or maybe your university or organization's high-performance compute cluster. You can access it from anywhere through these APIs. And then within Google Cloud, many of these tools and services are integrated with each other. So it makes it easy to do things like write streaming data pipelines, computer analyze data at the source without having to think about servers or data management. Those are the main two options, and they're not mutually exclusive. We operate fully in the cloud, but we use a lot of their APIs to make calls. So just to demonstrate a little bit about the ease of use of these APIs and what this means. So for starters, we as a broker do not have to write our own APIs, and other brokers do. So what this means is that the end users of our brokers don't have to rely on us to write and maintain a good API. It is already a well-developed and supported thing that is developed and supported by Google engineers. So we do provide tutorials. We provide Python wrappers to make it a little bit more straightforward to access our Pitt-Google specific resources. Here's another example of the ease of integrating using these APIs. So this is something I threw together. This is our integration with the Tom Toolkit. So if you're not familiar with the Tom Toolkit, it is a software platform that is specifically designed to support bringing together astronomical data, doing some analysis and triggering follow-up on different telescopes and doing coordination and scientific collaboration. And so I threw together, this is actually Tom Toolkit 3 ways. So I'm connecting to our live message streams in 2 different ways. One's a REST API, one's a Python client, and I'm connecting to our database client. These are just proof of concept things. We will pick and just do a straightforward implementation, but the point is that it's simple to integrate these things with external services. Some other things to be aware of. When you're operating this way in Google Cloud, there are quotas and limits. So we haven't run into too much of an issue with this the quotas and limits are generally high, but some of these might be an issue at LSST scale. So if you're looking into operating in Google Cloud, that's just something to be aware of if you are really doing high loads. Let's see. Yeah, I think that's good for this slide. So the cost model is really different than what other brokers do. So what is the Google Cloud cost model? First of all, it's free to connect, test things out. It's free to run ongoing analysis at low volume, low from LSST perspective. Different things that support that. There's a $300 credit for new accounts. And then there are free tier quotas that renew monthly for everyone. So for example, BigQuery is a data warehouse. The first 1 terabyte of data processed when you're querying that is free every month. So you can query 1 terabyte of data for free every month here. Beyond the free stuff, everyone pays for what they use. Pay as you go, no upfront costs. So here is a more specific example of what that means. So we store data in BigQuery. So we pay to store it. We pay to query it ourselves. Our end users pay for their own queries on the data that we have stored. So that's one of the things that we mean by everyone pays for what they use. The costs are broken down to a fine level of detail. Here are a few examples. You can always look at these pricings. Yeah, okay. One thing to watch out for is egress charges. So if you're moving data between Google Cloud regions, there are egress charges, and those can be kind of expensive. So that's something to be aware of. So in those cases, you would consider computing next to the data and maybe just pulling down a limited subset of data after you do your compute. So the trade-offs: you're paying a cloud provider to manage the infrastructure, run your job, store your data. You are not paying basically people in your organization. You are not paying for the personnel time to plan, develop, manage, and support most of the infrastructure. You're not paying to purchase hardware. You're not paying for network bandwidth, things like that. So this is just something to consider. Different organizational budgets are scoped for different things. So you might have a budget that has specific FTE hours, human hours, to pay your personnel, but it doesn't have money to pay a cloud provider. So that is one of the things that I've kind of run into and wanted to mention as a trade-off. Okay, so let's look a little bit more at our architecture, what our broker is actually doing, and then I'll describe some of these Google Cloud services that we are using. So this is just a really high-level overview to get us sort of conceptually thinking about our pipeline. So the alerts come in from an external survey. We are currently running on the ZTF stream, and of course, we are developing towards LSST. So the alerts come in here to our consumer module. The consumer then passes them to some data storage modules and to the science pipeline. And this data is passed through PubSub. PubSub is a message delivery service and also API calls. The users sit here right in the middle, and they are here in the middle in this diagram on purpose. And the reason is that we expose all of this data at every step, and I'm going to fill in the details a little bit so you'll see a little bit more specifically what this means. But the data is exposed everywhere, so it comes in first from into our consumer. Users can get this straight away. They don't have to wait for any of this stuff. They could access the full stream right away if they wanted to. They can query databases or object storage as soon as that stuff gets in there. They can listen at various levels of our science pipeline. Okay, so now I'm filling in the details of what our current pipeline actually looks like. And now I'm going to take away these bounding boxes. These bounding boxes really are just conceptual. So in other words, I'll flip back here for a second. With a more traditional design model, this stuff would be all packaged together into a container and run on a cluster of VMs. This would be packaged into a container and run on a cluster of VMs and so forth. That is not what we do here. What we do here really looks like this. Each of these modules, and each module is in this red compute card. Each of these modules is deployed independently and runs totally separately. So this file storage module is no more connected to the database storage module than it is to any of the science modules or anything else. And same here, these are deployed and running independently. The data transfer happens through PubSub and API calls. And this PubSub stuff is all automatic. So our consumer immediately dumps the alerts to a PubSub topic. This is a public PubSub topic. Anybody can sit here and subscribe to this, and they can get it at the same time that we do. So our other modules sit here and listen to this public topic. And then we use these cloud functions, which are serverless compute. They are automatically triggered by messages that come into these PubSub subscriptions. They do their processing, and then they jump to public resources. They push their results to public data resources, so PubSub topics, and also BigQuery tables. BigQuery, again, is a database-like storage. So this is an event-driven microservices model. This is the second thing that makes our broker really unique, in addition to taking explicit advantage of explicitly cloud-based services. This is an event-driven microservices model. So what does that mean? Microservices is an architectural style that structures an application as a collection of services that are loosely coupled, independently deployable. So that's what we have here. This event-driven piece, well, events in our case are alerts or messages, and so this is per message processing. We are not doing any batching at all, which is, I think, as far as I know, unique among brokers. The benefits of this. It's really fast, lightweight. We do not manage any clusters of VMs. This is per alert processing. It's easy to think about and develop. So when you're writing your pipeline processing, all you have to think about is operating on the contents of one single alert packet. It's highly fault tolerant. Fails are automatically redelivered by PubSub. Other messages are not affected. Because it's just per alert processing. This scales from 0 automatically and nearly instantaneously to meet the incoming demand. Drawbacks. One major drawback that we have run into so far that we are trying to work out here is cross matches. So it's pretty common to want to, so these alerts are coming in. We want to do basically a cone search with an external static catalog and identify, maybe we cross-match with Gaia, and so we can identify alerts in the LSST stream that have already been observed by Gaia and may have a specific like variable star classification and things like that. So this is a challenge within an event-driven pipeline. We can't really query an external service like CDS 10 million times per night. In other words, it would just be rude to query CDS on every single alert. They'd probably end up blocking us. It is also expensive to do per alert lookups in BigQuery. And so we may actually end up batching this portion of our pipeline to get around this. So to talk a little bit about some of these services in a little bit more detail, PubSub, as I had mentioned, is a streaming message service. This is similar to Apache Kafka, but a lot less management from our end. It's asynchronous publish subscribe. Publishers are totally decoupled from subscribers. Let's see, a couple things that I'll point out. PubSub has push subscriptions. This is not something that Apache Kafka has. So every other alert broker uses Apache Kafka for their streaming message service. We are the only ones who use PubSub. So this pushing to an HTTP endpoint, this is how our pipeline is actually driven. So these are push subscriptions to any HTTP endpoint that can receive an HTTP request. And then, of course, you can pull these from anywhere using these APIs, as I kind of showed you with the Tom toolkit. So just a little bit about pricing. The first 10 gigabytes per month is free in terms of the throughput from PubSub if you want to sit there and listen to these streams. After that, it's $40 per terabyte. So here's an example of egress that I wanted to show you that can get expensive. So it's something to watch out for. So if you are crossing Google Cloud regions with this throughput, this can be at least twice as expensive as the actual throughput itself. And so in that case, if you're really wanting to move a lot of data, you might want to consider computing next to the data first and then only pulling down a limited subset. There are no storage fees unless you turn on special retention options. There's some pricing. Okay, BigQuery is a fully managed data warehouse. So this is a database like, it supports SQL queries. This is columnar storage. It's optimized specifically for complex analytical queries on large data sets. This is what BigQuery is really good at. So this is great for LSST scale. So BigQuery might actually be something that you all are interested in exploring in terms of your IDAC. It might be a simple way for you to provide, even if it's not your main database, it might be a simple way for you to get some of this data into Google Cloud in a way that lets people play with it. And I'll show you a couple more options for doing some analysis and playing with the data in BigQuery. One thing that is different than many databases, there are no indexes in BigQuery. This will do a full column scan for every query. And so that's why single point lookups are quite expensive. You can reduce this by partitioning and clustering the tables. That's something to look out for. Okay, so let's look at a couple more architecture diagrams here. We'll start just with the one we've already seen. This is our currently running pipeline. And now I'll flip to what we are working towards in the near future. And so mostly the differences here are in the science pipeline. So we're going to, we have immediate plans to add several things here. This semantic compression just reduces the amount of data in the alert packet. And so if somebody wants to listen to the full stream, but have it be much less costly, both in terms of data volume and actual money, they could listen to this stream. So this is like, what are the 10 to 100 numbers that best characterize this alert that will be most important and useful for scientific analysis? And then we'll drop everything else just to lighten those packets. Cross-matching with Allwise, I'm working on putting this in. I've done some tests and things, but as I mentioned, we have some things to work out with this cross-match. And these are things that we are currently doing already, classifying with the Super NNOVA classifier, which was developed by some of the Think broker people, notably Anaïs Moller. The other thing that's different about this is moving from, I'll flip back a little bit, from Cloud Functions in each of these cases to Cloud Run. These are both serverless compute, but for a few reasons, we think that Cloud Run is going to be more beneficial at LSST scale. So that's the near future. A little bit longer term future looks kind of like this. So a couple of things I'll point out are actually the thing that I'll point out here in the science pipeline is this level of filters here at the end. And so we are imagining a lot of use cases where they don't actually want to listen to 10 million alerts per night. They want a more limited subset. We want to enable this kind of science. We don't want to make everyone listen to all the data. We want to, and we have specific plans to put in some of these filtering options. And the idea is to be sort of generous about what passes so that we're not filtering out a bunch of things that you want. So the sample will be less pure, but better for your own scientific analysis, you meaning the end user. And this is more specific examples of where the user sits and how this works. So a couple of things, they might listen to one of these PubSub topics that's been filtered here, run it through a little bit of compute, and store it in their own BigQuery table. They might want to listen to this full stream and do a classification, run their actual own classifier on this full stream. They can also sit here and listen to, or excuse me, query any of these BigQuery tables. These are sort of direct storage, and then there is also BigQuery storage at some different steps of the pipeline after we cross-match, after we classify. So filters on PubSub streams, I think I'm actually going to skip through some of that. Cloud Functions and Cloud Run, this is serverless compute. Different reasons to prefer one versus the other. Cloud Functions is much simpler. You just write the function and deploy it. I mentioned this earlier. Cloud Run, this is serverless computing that allows you to run containers that are triggered by requests, or in other words, that are triggered by alerts. So both of these things get triggered by HTTP requests, and this is event-driven processing in both cases. Cloud Run should handle the LSST load a little bit better, and you have a little bit more control because you are containerizing this yourself, so you can control the environment and things like that. Our consumer, this is the only VM that we run, and it's just a single VM. It's a very small VM. It's actually a shared core, half a virtual CPU, less than 2 gigs of memory. All this does is pass through the Kafka stream into a PubSub stream. So from LSST or ZTF, they produce a Kafka alert stream. We just immediately turn it into a PubSub stream. Okay, so I'll show you a little bit of some processing times and maybe some things to take away from this. So these are different modules in our pipeline: consumer, storing in BigQuery, cross-matching with Allwise. This is not live right now, but I did a few tests, and so here's the results of this. And then classifying with SuperNova. The first thing to notice is that this is really fast. So here on the y-axis, this is the time delta between. Well, this is the processing time for that specific module. So most of these are around 1 second or less. So this is really fast. We don't think that anybody is going to care that it is this fast. You know, there are certainly many science use cases that are time sensitive, and that is the whole reason for the alert stream format. But the vast majority of the time-sensitive cases are not so time-sensitive that they care about, 1 second versus 10 minutes, for example. And so we don't think that anyone is necessarily going to care that it is this fast, but that is a bonus. One thing to notice here is that the alert rate doesn't really care, or excuse me, the processing rate, the amount of time it takes to process through these, doesn't really care about what the actual alert rate is. So these marginal histograms here give the alert rate through the module per minute. And you can see that it's not wildly different when the alert rate is high versus when the alert rate is low. This cross-match with all-wise takes much longer than the other ones. This has to do with the query on BigQuery. Just doing this kind of shows you that the query for individual alerts on BigQuery is just expensive. And it's expensive both in time and in cost, actually. In terms of how this will handle the LSST scale, there was sort of a serendipitous test where the alerts were delayed coming from ZTF for about an hour and a half. And so this big delay that you see here comes from ZTF. And you can see that the incoming rate is almost 20,000 per minute. So this is a factor of 10, I'll flash back, a factor of 10 higher than what's normal for ZTF. This is much closer to what's going to happen for LSST. So we had this brief period, about 10 minutes, where we streamed a bunch of alerts in at LSST scale, and you can kind of see what happens here. So this store in BigQuery, this has a high delay. This goes up from 1 second previously all the way up here to 10 minutes or something. This has to do with a quota on API calls. So it is actually not the streaming insert API call. It's actually a get table API call that happens with each streaming insert. So this is an example of where some of these limits and quotas might affect us at LSST scale. So we need to kind of figure out how to not make so many API calls here. Again, the streaming inserts is fine, but the get table is not. So we just need to do the get table less often. And this one just shows you that it's not actually the cloud function itself that's causing this big delay. The cloud function itself handles this just fine. Okay, so right here at the end here, I'm going to talk about a few of the other Google Cloud tools that look interesting and that I think might be of interest to you all with the IDAC. I looked through like your working groups and the different people who have given you talks in these webinars, and I concluded that probably most of your use cases are going to be more catalog oriented and less live stream oriented. And so I've got 3 things here that I'll show you that are related to using BigQuery that you might be interested in. These are all things that I'm interested in exploring more, but I've only looked at kind of at the surface. So TAP and ADQL, these are things developed by the International Virtual Observatory Alliance. So they are specific for astronomy. They, a lot of astronomers know TAP and ADQL. ADQL is similar to SQL, but has some specific things that are useful for astronomy. This is used in the Rubin Science platform. So it was announced at the 2020 AAS meeting that TAP and ADQL are coming to BigQuery. This is currently under development by a private group in collaboration with Google. If you're interested in this, I can get you in touch with them. Next thing here is BigQuery ML. So BigQuery actually has machine learning built right in. You can create and execute machine learning models using standard SQL queries. So this is definitely compute at the data, literally. So this is an example query. This is just something from the Google Docs London bicycle hires k-means example. So this is a SQL query that is creating a k-means model. And then you can do another SQL query to validate the model and so on. So that looks interesting. And the last thing I'll show you here is BigQuery plus Data Studio. So this is just a little example that I did really quick. I am interested in CVs, cataclysmic variable stars, and dwarf. So this is, I wanted to basically look at what does a known dwarf nova light curve look like in ZTF. And so I come here. This is a preview of the BigQuery table, our DIA source table. So this is actually our table. So you can do just a free preview of the table by going onto the Google Cloud console. You can do a query right there if you want. Of course, you can also query outside. So I do a query to pull down a known dwarf nova, and then I click this button that's Explore with Data Studio. And I get this area that I can play with the data and do various plotting and analysis type stuff right here on the Google Cloud console without having to pull any of the data down or anything. So both this BigQuery plus Data Studio and BigQuery machine learning seem like things that could be very convenient and easy for some quick looking at the data, quick analysis, train up a quick machine learning model and just see what it looks like. Maybe you then want to take that and refine it on your own compute somewhere. But both of these things can make it easy, for example, for someone like you all developing an IDAC, to just put this data in BigQuery and then let people use these tools that have already been developed, and you wouldn't have to support all of this stuff. Your users could just come on and access it this way. Okay, so thanks for listening. I will just leave this up with a selection of takeaways from this talk, and I'll stop there and take any questions.
Well, thank you very much, Troy, for the very interesting talk. Now we have a few minutes for questions. If you joined us on YouTube, please post your questions in the comment section. And if you joined us here in Zoom, please raise your hand and ask your question. So questions?
I have dozens of questions. I mean, that's the problem. No, let me try to simplify. I have two questions. I mean, of course, cloud is tantalizing. Everybody, you hear about it. That's the dreamland, right? Fantastic. You don't have to worry. You don't have to pay people. All the benefits that you can imagine. But however, there are two issues. I mean, looking at what you guys did, it suggests that you probably had to have a very strong contact with the software engineers at the cloud, right? I mean, to actually make all this setup. How long did it take? What is the overhead of building something as complex as this in the cloud? And the second question is how long it took to the cost analysis, because that's the whole issue, right? I mean, to really understand your use cases and see where the benefits are. Because in some cases, like you said, in our case here in South America, if we want to bring the data over, we're already paying a lot of money. And also, something that always troubles me is that how are we going to get the data? If it's cloud to cloud, who is going to pay? So there are a lot of little issues that Will has already raised at different points that makes me worry to make which direction we should take. But let's just simplify the setup time and the cost analysis.
Yeah, great questions. Those, okay, so let's see. In terms of setup time, it has and just the effort involved in setting this up. It has certainly been useful to have contacts at Google to be able to chat with them about, you know, how would you recommend we implement if, you know, for this particular use case with this kind of pipeline at these rates and things. So that has been useful for sure, but I would say that it's not necessary in order to build this. The documentation that Google provides online is very thorough, and the tools are simple enough for, you know, someone like me who 3 years ago was just starting with Python and didn't really know anything about cloud computing or anything to go ahead and set this up. So that's one thing. In terms of how long, it's so let's see, we have a small collaboration. We're basically, you know, 3 grad students working on this, plus our advisor and our contact at Google. But actually, none of us have been funded to work on this until this semester. So this semester is actually the first time. And so we've all been doing other things in addition to developing this. And so actually the development time is probably a lot less than you might think based on looking at the number of people we have working on it. And you know, we've been doing this for a couple of years.
But who built the classifiers and everything?
Oh, I mean, yeah, so that's one thing. We have not developed any in-house science analysis directly ourselves. So the classifier.
Okay, so you're plugging in. Okay.
Yeah, right.
Okay.
Yeah.
And you're fully functional. Are you really already analyze the CTF?
Yeah.
Now, another question, a quick question. I mean, if I just want to be, just pick up your streams, do I have to pay?
Yes.
And how do I know how much I'm paying for?
Yeah, for sure. I can, so a couple of things. One, there is a pricing tool that is that's available on the Google Cloud Docs that you can plug in. You know, I want to do this, this, and this, and it'll kind of give you an estimate. That's one thing. I can certainly give you, if you're interested, you can shoot me an email or something, and I can, or you know, I can write it down.
No,
I can get you a better cost analysis. I actually wanted to show you something, and I had a little bug in my billing plotting code that I just didn't get to working out. So I can definitely send you that. I know that would be interesting.
I don't want to be obnoxious, but let me make a final question. Why would I go there and not go to a free one, Antares, for instance, or Think, or Alerts? Why would I choose you?
Yeah. Yeah. Okay. So
I don't want to be obnoxious. Okay, just.
Oh yeah, no. It's a totally valid question.
Yeah.
Certainly, the egress charges, so the actual data transfer charges, can be prohibitive, and so I would not really recommend that you sit in Brazil and pull all the data from us down to you. I'm sure that there are more cost-effective ways to transfer large amounts of data like that. But you can certainly listen to our streams and do some compute in Google Cloud next to the data. So you're not paying any egress charges at all.
So this probably would be the interesting part, right? I mean, to actually be able to access and process the data at the cloud there, not, okay.
Yeah.
Thank you. We should perhaps continue the conversation in another venue.
Sure, thanks. Yeah, great questions, yeah.
Thank you, Luis. More questions? Well, I have some questions. I will try to be summarize my questions. If you showed us some screens, and I'm thinking as a user, how should I think building my functions, what kind of language are you using? For instance, can I write can I consult directly into the databases from a Jupyter notebook, or do I need to be logged in some kind of screen on Google services?
So our pipeline is predominantly written in Python.
Yeah.
And so all of these APIs have Python clients. And so is that your primary language or not? You meaning all the
yes, for me, yes.
Yes. Okay,
we can say that. Yeah.
Okay. Yeah, that's the most common in astronomy, so I kind of assume. Yeah. So I'm sorry. What was the other piece of your question?
It was if I can actually access that directly from Jupyter notebooks, do my queries, or if I need to be logged into some kind of Google service.
So what you need in order to access this is an account with Google Cloud and just service credentials that you create yourself and download. And so once you have that, you can do this from anywhere. So you can certainly do it from within Jupyter Notebooks or anywhere else. Some of these things have specific integrations with things like Jupyter Notebooks. So like BigQuery ML, for example, has a specific integration with Jupyter Notebooks that makes that simple. So there are things like that.
Okay, well, thank you. And another question is, you showed some that in a slide that you wouldn't actually filter the 10 million alerts because it would be too much, and then you showed some cases like variable stars and some kinds of transients. My question is, are you interested or in maybe filter some solar system information, or are you just
oh yes, absolutely. So these let's see, to kind of clarify one of your first points, we certainly will apply filters. So all of these PubSub topics are public. These ones up here will include the full stream, but down here we will put a level of filters so that each stream coming out of here, and this is 4 different streams, will be significantly filtered down. So it'd be a lot less data to listen to. So one of these streams is just likely extragalactic transients. One of them will be likely supernova, and so on. In terms of like solar system objects, yes, that is the kind of thing that we are certainly interested in. The things that I've listed here are things that we in our group have more specific scientific interests in, and so that's what I've listed.
Sure.
But we certainly do want to support all of these major LSSD science areas, and so I certainly in the future these kinds of filters will include things like solar system objects. And if that's something that you're interested in, we would certainly be interested in working with you to just write a simple filter and throw it in here.
Okay. Well, thank you very much. Well, we are a little bit behind schedule. If there is a last question, I think we can allow it. All right, if there are no more questions, then I think we will now wrap this up. This presentation will be available on our website and on LIneA's YouTube channel. And for the next week's webinar, we will have joining us David Trilling from the Northern Arizona University, continuing in our series on LSSD brokers. And he will be talking about the solar system notification alert processing system. Thank you everyone for attending, and a special thanks to Troy. Thank you, Troy.
Thanks for inviting me. I appreciate it.
So everyone, have a great day, stay safe, and I hope to see you all back again next week. Thank you. Bye-bye.